there is a number you have almost certainly never thought about. It is 4. 4 degrees Celsius. At this temperature, not at zero, not at the freezing point, water reaches its maximum density. It is heavier at 4 degrees than it is at any other temperature. If that sounds like a piece of trivia, it isn't. It is the reason lakes freeze from the top down instead of from the bottom up. It is the reason fish survive winter. And it is the first clue that water is not a normal liquid. The story begins with what water actually is. A water molecule is simple. 1 oxygen atom, 2 hydrogen atoms, bent into a V shape. That bend matters because it creates a molecule with 2 different electrical poles. The oxygen side is slightly negative. The hydrogen side is slightly positive. When water molecules are near each other, these opposite charges attract. A hydrogen atom from one molecule is drawn toward the oxygen of a neighboring molecule. This attraction is called a hydrogen bond. It is weaker than a full chemical bond and far more fleeting, but it is the reason water behaves like nothing else on the periodic table. In liquid water, hydrogen bonds are constantly forming and breaking. Molecules jostle, connect for an instant, then separate and find new partners. This chaos allows molecules to pack quite closely together, so liquid water is relatively dense. But as water cools, the molecules slow down and the hydrogen bonds become more persistent. Around that same 4 degrees Celsius, the liquid reaches its densest possible arrangement, the sweet spot where molecules sit close but are still mobile. Below that point, the approaching freeze starts forcing molecules into a specific geometry. Recent computational modeling, published in 2026, reproduced this exact density peak by simulating how short-range molecular ordering collapses just before freezing, confirming decades of experimental measurement with a fully modeled mechanism. Then, at 0 degrees, the geometry locks. Every water molecule in ice ends up hydrogen bonded to exactly 4 neighbors, with those bonds pointing toward the corners of an imaginary tetrahedron, a shape like a pyramid with a triangular base. When that arrangement repeats across billions of molecules, it forms a hexagonal crystal lattice, a 6-sided honeycomb of water molecules held open by hydrogen bonds. A 2021 study of hydrogen bond behavior across this exact temperature range found the bonds becoming measurably more stable and longer-lived as the freezing point approaches, which is the microscopic reason the lattice is able to lock into place at all. That word, open, is the key. The hexagonal lattice contains empty space. The molecules in ice sit farther apart, on average, than they do in liquid water. So when water freezes, it expands. Ice occupies about 9% more volume than the same mass of liquid water at the freezing point. If you have ever put a glass bottle of water in the freezer and found it shattered the next morning, you have met that 9% directly. Now compare this to almost any other liquid. In a typical substance, atoms or molecules pack more tightly in the solid state than they do in the liquid state. The ordered crystal is denser than the disordered liquid. Solid wax sinks in liquid wax. Solid metal sinks in molten metal. This is the normal behavior, and it makes intuitive sense. Things get denser as they get colder. Water breaks that rule because of the hydrogen bond. The same attraction that gives water its unusually high boiling point and strong surface tension also imposes the open crystal structure that makes ice float. A small number of other substances also expand on freezing, gallium and silicon and bismuth among them, but water is the only one that shapes the living world at this scale. That shaping begins at the surface of a lake. Picture a lake in autumn. The air cools, and the surface water cools with it. Cold water, approaching 4 degrees, becomes denser than the warmer water below it, so it sinks. That sinking draws warmer water upward, which cools in turn and sinks again. The lake convects, mixing itself until every layer, from top to bottom, reaches 4 degrees Celsius. Now the lake is uniform, every molecule at its densest possible temperature. The surface keeps cooling. Below 4 degrees, water does something a normal liquid never would. It becomes less dense. The colder surface water no longer sinks. It stays on top, and as the temperature drops toward zero, that surface layer keeps expanding and lightening until it freezes. A sheet of ice forms. It floats. Beneath it, the rest of the lake stays liquid. This is the pattern for most temperate lakes that experience a real winter. Shallow lakes, tropical lakes, and salt lakes each follow their own variations, but the top-down freeze described here is the rule across a huge share of the freshwater lakes in the Northern Hemisphere. This is also the moment where water's strangeness becomes a matter of life and death. The ice layer insulates the water below, slowing further heat loss. Through the winter, beneath the frozen surface, the lake holds steady at around 4 degrees Celsius, its temperature of maximum density and greatest stability. Fish, amphibians, aquatic insects, and countless microorganisms survive in that liquid sanctuary, sealed beneath the ice, waiting for spring. If water behaved like a normal liquid, the coldest water would be the densest, and it would sink immediately. Lakes would freeze solid from the bottom upward, and in any climate with a real winter, freshwater life as we know it would not exist. But the consequences don't stop at the shoreline. Ice floats, which means it accumulates at the surface of the planet rather than at the bottom of the ocean. And ice at the surface does something crucial. It reflects sunlight. Fresh snow and clean ice reflect somewhere around 80 to 90% of the solar radiation that hits them. Open ocean water, by contrast, reflects only around 6% and absorbs almost everything else. Scientists call this reflectivity albedo, and it creates a powerful feedback loop. Ice reflects sunlight, which keeps the poles cold. Cold poles sustain more ice, which reflects more sunlight. Climate modeling on this feedback, including work published in 2013, shows just how strongly a high albedo surface can amplify cooling at a planet's poles. If ice sank instead of floating, that feedback would break down. Winter ice would form, sink into the dark depths, and leave behind open water that absorbs far more solar energy, making persistent polar ice caps dramatically harder to form and maintain. To be fair, the primary reason the poles are cold in the first place is latitude. They simply receive less direct sunlight than the equator does, and that fundamental fact would not change if ice sank. But the ice albedo feedback amplifies that cooling. It takes a region that would be cold anyway and makes it colder still. The difference between a feedback that works and one that doesn't is the difference between a planet with bright white caps at each end and one without them. If water were an ordinary liquid, if the hydrogen bond simply didn't exist, and ice sank like almost everything else does, Earth would still have seasons and still have cold poles, but it would not have the persistent reflective ice sheets that have shaped this planet's climate through ice ages and warm periods alike. The global climate system that produced the world we live in would not exist in the same form. A hydrogen bond is a weak thing. It forms and breaks in trillionths of a second, but it forces water molecules into a shape that makes ice float. Floating ice insulates lakes and lets freshwater life survive winter, and floating ice builds the reflective polar caps that help cool the entire planet. All of it traces back to the bent shape of a single water molecule and the small electrical charges sitting on its atoms. The next time you see ice floating in a glass of water, you are not looking at a simple solid. You're looking at the molecular reason life survives winter on Earth. This is reasonable wonder. Big questions. Clear science.